Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the second one. This lesson is divided into several parts.
Recall that the heat diffusion equation is a complex differential equation in partial derivatives. However, it can be simplified for one-dimensional, steady-state conduction. Even more for solids without internal heat generation and constant thermal conductivity. From the temperature distribution, applying Fourier's law, the one-dimensional heat transfer rate in a steady state can be found.
Let's start by defining what thermal resistances are.
At this point, for the special case of one-dimensional heat transfer with no internal energy generation and with constant properties, a very important concept is suggested by the heat transfer rate equation. In particular, there exists an analogy between the diffusion of heat and electricity. In the same way as an electrical resistance is associated with the conduction of electricity, a thermal resistance may be associated with the conduction of heat. Defining resistance as the ratio of a driving potential, delta T, to the corresponding transfer rate, Q, we can find the thermal resistance for different simple geometries. For a plane wall, in steady state, without internal heat generation, uniform and constant thermal conductivity and with one-dimensional heat flux, the thermal resistance is the wall thickness divided by the thermal conductivity and the cross-sectional area. Notice that the wall cross-section must be also constant. The specific thermal resistance is defined per unit of cross-sectional area. For a cylindrical wall, in steady state, without internal heat generation, uniform and constant thermal conductivity and with one-dimensional heat flux in the radial direction, the thermal resistance is the natural logarithm of the external radius divided by the internal radius. All this, divided by 2 times pi times lambda times L. For a spherical wall, in steady state, without internal heat generation, uniform and constant thermal conductivity and with one-dimensional heat flux in the radial direction, the thermal resistance is function of the thermal conductivity and the internal and the external radius. Let's do the same with the boundary conditions, that is with convection and radiation in the outer surface. Applying the Newton law in the surface of contact between a solid and a fluid. The thermal resistance is the inverse of the product of the convection coefficient times the surface area. The specific thermal resistance is defined per unit of contact surface area. Heat losses by radiation in the surface of a solid to a very big surface or surroundings can be calculated with this equation. However, this resistance depends on the surface temperature. Therefore, it is not a practical approach. We will discuss this more in detail when solving problems of insulation.
Let's apply the concept of thermal resistance to solve problems with composite walls.
Thanks to the utilization of thermal resistances, calculation of composite walls is very easy. For a plane wall, with convection in both sides, the equivalent thermal circuit is composed by a set of thermal resistances in series. Like in electrical circuits, we can sum resistances connected in series to obtain the equivalent resistance. In this way, the heat flux can be written as a function of the inlet and outlet temperature and the thermal resistances of convection and conduction. For a composite cylindrical wall, like in the composite flat wall, the heat transfer rate may be expressed as the difference of inner and outer temperatures divided by the sum of thermal resistances in series. Observe that the areas and radius for each resistance are different.
Let's apply the concept of thermal resistance to solve problems with bad thermal contact between surfaces.
Although neglected until now, It is important to recognize that, in composite systems, the temperature drop across the interface between materials may be appreciable. Per unit area of the interface, the contact resistance is defined as the ratio between the temperature difference and the heat flux in the contact surface. You can find typical values of contact resistances in the literature.